Hello and welcome everybody. This is chapter number 8, second order circuits of our Sadiku's textbook. It is the continuation of the previous lecture. In our previous lecture, we talked about how we use or how we calculate the initial values for a circuit, especially circuits having two storage elements. So in this lecture, we will be talking about how we solve a source-free RLC series circuit. So in here we see a series combination of resistor, inductor, and capacitor. Again, remember that this is a source-free RLC circuit. In this circuit, we do not have any voltage or current source, or we can say that any independent or dependent current source is attached in this circuit. This circuit practically represents a system in which where we have an inductor that is completely magnetized and a capacitor that is completely charged, and this sort of combination or this sort of situation arises in practical circuits where we want to check the response of such a combination of elements, where we have a charged inductor and where we have a magnetized inductor and a charged capacitor. So in this case, or in this special case, we are given the initial conditions. We have two initial conditions. The voltage is basically the capacitor voltage. It is against the capacitor, and the current, and that is the current that is stored in an inductor, or you can, in some books it is also written as IL and VC. So the initial conditions for this circuit for the inductor and capacitor are given, and the resistance is the third element in here. So let's try to solve this circuit. In first case, we try to develop the differential equation, and we'll see how we analyze or how we calculate the solution for that and for our developed differential equation. Remember, this is a second order circuit because we have two storage elements and a resistor attached to it. So let's start. So first of all, we know that the current I is flowing in this circuit, and the loop equation. So we can just simply write the loop equation. So for the loop equation for I becomes I times R plus inductance times di by dt, or basically we are finding out the voltage across this resistor, voltage across this inductor, and the voltage across this capacitor, and the sum of all these voltages is equal to 0. So VR plus VL plus VC will equal to 0. So VL is, again, remember, di by dt plus VC 1 by C minus infinity 2 times t, I with an integration variable. Remember, the integration variable changes in this case. You can call it tau. So this is the differential equation or the loop equation for this circuit. So if we are going to simplify, if in one manner we want to simplify this equation, this equation can be simplified, or we can just simply differentiate the equation 1. So if we differentiate the equation 1, we get R times di by dt. So remember, I is the variable here. Inductance times di by dt square plus I by C equals to 0. So this is the differentiated form of this equation, and we can also always simplify this equation to say the actual second order form, or a simplified second order form. This is L di by dt plus I by C equals to 0. This is, you can, in a way, yeah, so a more simplified form for us. So I call it equation 3. So this is how we develop the initial differential equations for this circuit. And remember, this is the second order differential equation because there is a second derivative of the variable I that is associated for this circuit. So let's try to solve and see what sort of and how we are going to solve this thing. So so what we have here, so from our equation 1, we can write that from equation 1. So from equation 1, or let me write it again. The equation 1 was IR plus L times di dt plus 1 by C minus infinity di times tau d tau equals to 0. So from equation 1, we just put the initial conditions here. And our initial conditions, again remembering VC 0 negative was equal to V naught, and IL 0 negative, oh sorry, 0 was I naught. And so just this equation will become I of 0. So at, you can say, time t equals to 0. 0 plus L di 0 by dt plus 1 by C again. So this is at time t equals to 0. So minus infinity to 0 I tau d tau equals to 0. So now using these values, and remember VC 0 negative was 1 by C minus infinity to 0 I times dt equals to V naught. So this is the same thing. So what we get over here is R times I naught plus L d by, we do not know this case, di by dt. We are so this is another initial condition that we are unaware of, not divided by C equals to 0. So oh sorry, this thing is equal to this. Oh, sorry, this is by C. Yes, this is V naught. So what we are left here is something like this. So if we try to simplify this, so this becomes minus V naught divided by L plus I naught. Again, this comes with a minus sign. So this is something which we get, and this again, if we simplify it, it comes out to be L E naught plus R into I naught. So remember, so this is a first order differential equation, and in other way we can say that this is another initial condition for the circuit which we at least need to solve it. So we not only need the initial value of current and voltage across inductor and capacitors respectively, but we also need the rate of change of voltage and rate of change of current in these components in order to properly solve this equation. So when we put the initial conditions in our second order differential equation, we get with the help of these two initial conditions, our second order differential equation reduced to a first order differential equation. So from so this is a simplified form of a first order differential equation, and from our observation and from our initial analysis in chapter number 7 of this textbook, where we solved the first order circuits, we are aware that the first order differential equations have certain form of solutions. So in this particular case, we can say that I of t a e power s t is a form of solution for this first order differential equation, or in a very simplified manner, we can write it as st is a general solution for this form of differential equation. In this general solution, we have where a and s are constants. So in this case, a and s are constants, and we have to basically find out the values of these constants in order to find out in order to find the actual solution for this thing. And this is what we have seen from when we solve the first order differential equations. So we know that this is a simplified or is a general solution for this case. So now we use this solution as a solution for second order differential equation and see what happens. So moving ahead, so we have when we solved our differential equation, remember equation number 3. Remember your equation 3. So equation 3 was d square I by dt square plus r by L di by dt plus I divided by LC equals to 0. So this one was our equation number 3, and our solution which we considered for previous case, or I equals to a e raised to power s t. This one was our one of the solutions for this differential equation. So let's put this solution in this differential equation and see what we get. So di square, replace I by e raised to power st plus r by L d by dt of a e power st plus I again a e power st divided by LC. This becomes equal to 0. So now we differentiated and take a few common factors and see how this overall equation simplifies. So if we double differentiate a e power st, it becomes a s square e power st, again e r by L a s e power st plus a e power s of t divided by LC from 0. So what we can take common? So we can take common a e power s of t. We can take common. So we are left with s square plus r by L into s plus 1 by LC. This is what we are left. So here we can see that if this equation, if we want to solve this equation, there can be either two solutions. Either a e power s of t is equal to 0, and the second case is s square plus r by L s plus 1 by under root LC equals to 0. So we are so in such a manner, we know that once one part is what we have assumed as our solution to our differential equation or second order differential equation. So we are more concerned with this s square r by L s plus 1 by under root 1 by LC. And here what we see that this part, this equation 2 is a quadratic equation. So if we solve this quadratic equation for s, we'll be getting two values of s, and those two values of s will basically give us two different solutions, or which satisfy this equation, or which basically satisfy the or which are basically you can say the two solutions for the second order differential equation. So so this is the quadratic equation we are left with is s plus 1 by LC equals to 0. So remember the formula, the solution for quadratic equation. Remember, so s is equal to minus b plus minus under root b square minus 4ac over 2a. So in this equation, from this equation, we can say that a is 1. We have b equals to r by L, and we have c equals to 1 by LC. So if we just use these values and so simplify it, we get say s1 and we get 1 2, sorry, s1 and s2. So there will be two solutions, s1 2. So it will be minus r by L plus minus under root r by L square minus 4 into 1 to 1 by LC, and we are divided by 2 into 1. So simplifying it, we are left with R by 2L. So this 2 comes here, plus minus under root. So you just take 4 common, and when it takes the under root outside, it becomes 2. 2 is outside over here, is this R divided by 4L, and so this is goes plus minus 1 by LC. So multiply and divide by 4. We have just taken 4 common from here. So what we are left? We are left with something like this. Minus R by 2L plus minus under root R by 2L square minus 1 by LC. Okay, so this is what we are left with. So simplifying it, we have we can replace we can call alpha equals to R by 2L, and we can call omega naught equals to 1 by under root LC. And there is another way of writing it like this. So take an under root and square. So this is basically the same thing. So this is one way of writing the solution. So basically, when we have a series RLC circuit, we have 2 values of S. So one value of S1 is minus alpha plus alpha square minus under root omega naught square equals to 0. And we have S2 as minus alpha minus under root alpha square minus omega naught square. So these are 2 values of alpha, and we can always remember, we can always put these values in terms of R and 2L as well. And this again, it goes up. It depends on you guys, that how you're going to solve it and how you're going to use it. So again, remember the units for alpha. Alpha is generally given in terms of nepers per meter, and omega naught is generally given as radians per second. Remember, omega naught is the undamped natural frequency of the circuit, and alpha is the damped or natural frequency for the circuit. These are the 2 different so not alpha is not the so S1 and S2 are basically the natural frequencies, or sorry, the damped natural frequencies of the circuit, whereas omega naught is the undamped natural frequency of the circuit. So we have S1 and S2. These are the natural frequencies of the circuit, natural frequencies of the circuit. So for this circuit, the natural frequencies are S1 and S2, and S1, 2 are given as, remember, minus alpha plus minus under root alpha square minus omega naught square, where alpha equals to R by 2L and omega naught is equal to 1 by under root LC. Okay, so this is one case, and we have omega naught is equal to and remember, this is the damped natural frequency, and omega naught is undamped natural frequency. And we can also call it resonant frequency. Resonant frequency. This is also, and this is again important thing to remember, that for any circuit or any second order circuit, there will be a resonant frequency that is called omega naught. And in either case, whether it's a parallel circuit or it's a series circuit, the value of omega naught will remain the same, and it is always omega naught equals to 1 by under root LC. And so eventually we get 2 values of S1 and S2. So we are Basically, we remember that I equals to E power st. So there are two possible solutions for this case. So one is the case where we have, say, a1 e raised to power s1t. Second one is a2 e raised to power s2t. Okay, so these are the two different cases. And remember, for values of a1 and a2, we need other initial conditions. To solve it. Basically, we need two things: I of 0, which basically we are given, and we are also required I of di by dt. So if we have these two equations, these two initial conditions, we can easily find the values of a1 and a2. So overall, the solution for I will become, it will be a sum of these two, or linear superposition. I1 equals to I1 plus I2, and this thing is equal to I1 equals to A1 e raised to power S1t plus A2 e raised to power S2t. This is the complete solution for a second order differential, for a second order circuit, or a second order source free RLC series circuit. So remember, and in this case, we have there are other three forms, or three types of further classification of this solution. One is underdamped, critically damped, and overdamped, and we'll be seeing those cases in our next videos. Thank you.